is sports biomechanics, and the talk is partially to help you guys get a handle on how we use this branch of mathematics in analyzing human movement. And the other half is for the people working in our lab, the new people, mostly Aaron and Evan, to gain some basic or fundamental understanding as to how the things you might have learned in your first, second year university, your vector linear algebra, how that relates to what we actually want to get at, which is quantifying how the body is moving. Okay. So mainly, what is sports and just general biomechanics? Kind of inherently, you have biomechanics. Historically, biology and physics mechanics, they kind of exist in separate domains of engineering and science. But it's really when people start to put that analytical lens onto human movement that this branch of research starts to emerge over the past couple hundred years. So the two topics I study are baseball pitching, which you have an example video. Participant's face is blurred out, as always, to protect their identity. And the other half is my personal passion project for years now, and that is dribble dunks. And for both of these movements, they are used somewhat frequently in sport, with often the outcome to drive performance. And then you can measure how well you perform in these while also understanding what the body goes through. And they are generally high stress and repetitive, which means they have implications for injuries as well. So there's a performance side, as always, and then there's an injury side. And almost all of sports biomechanics research has goals or focuses to either or both of these topics. And the fundamental backbone behind achieving these goals are your ability and desire to quantify and understand these movements, to understand the cause and effects, and then how things happen. But how does that tie with the mathematics that I want to talk about? So what is special about linear algebra? Right, so have no left, the simple algebra, probably the very first equation anyone's ever learned is 1 plus 1, and what does that equal to? Two apples, right? Boom. And usually we refer to them as scalar. It's a representation of a real physical quantity. You take one plate, grab another plate, you have two plates, no matter how you are holding that plate. Right? Even though the apple is upside down, it's still an apple that you have. Now, in the linear algebra or the vector algebra sense, what would you get? If you have an up apple and a down apple, you get a black hole. I'm just kidding. You get a 0. But they do cancel each other out if you account for their directions, right? So linear algebra essentially accounts for not only the size and the magnitude, etc. So it's more than just a simple quantity. It gives you more information that ties to it. But in order to utilize that more information you get, you have to define more things in the beginning. So here's an example. Say I'm hungry, I'm working, and I want to get lunch in Karma Cafe. And you want to, instead of you doing it, you want to give your job to a robot. You're like, okay, here's where I am. Here's Karma Cafe. How would you tell the robot to do the job? Obviously, they cannot just charge straight through the residential buildings. So you need to tell them, okay, go down Hudson Road, go across 5th Street, come back on Washington, right? But to know, for the robot to know, which way is down Hudson, is it going down this way or that way, you have to further define a signage. You have to say, go down Hudson, and that in this case can be a negative, and then go towards Washington Street. In that case, it's a positive, right? So once you set the signage and the directions, you can really specify where things are going. That's the whole essence of vectors. And in high school, you probably learned vectors are special because they have a directions and distance, right? A magnitude and a direction. That's usually what people say. But in order to quantify distance, you also need an origin. That's usually the missing third point. So that was a 2D example, right? Top-down view, but we live in a 3D universe with the slides being on the 2D screen. So typically we have to define 3 directions. And these 3 directions essentially define all motion in 3D space, having these three vectors that are 90 degrees from each other, which is their special mathematical quality. There is more than one way. Have you guys heard of like polar coordinates, where instead you use angles of inclination and the other thing to define the 3D position? This is just one of the ways. And in terms of what we are working with here, human movements, that's sufficient. In some crazier branches of engineering where you have rotating arms or orbits around a star, polar coordinates might be better. And what's even nicer is that when we set up our camera system that we use to capture the movements, a coordinate system is already provided. That's the lab coordinate system that tells the cameras and the lab what's the relationship between them. It allows the cameras to know, okay, this way is Z, that way is X, and up is Y. But that comes with your motion capture engineering software, and sometimes it aligns with the movements you're studying. In this case, I know it's hard to tell, but this is actually the setup for the baseball pitching research, in which case you see the direction of pitching is directly aligned with one of the axes that comes with the setup. So luckily, you have your directions already defined, so if you study easy things, you don't need to do anything to the directions. It's already there. But most things we do aren't easy. And I'll show you an example why. Because once I got done with this project, I was like, hey, it's easy to study 2-foot running jumps, right? It's the same, you run up, you jump, you take off, and you dunk. But then one thing I found is that I tried my best to align these force plates, but you see the jump, when you're on the ground, it's here, closer towards the center of the plate. But as you take off, there is a lateral movement, okay? So the forward trajectory of the body, especially during flight, is not the same forward as the forward defined by the lab space. So here's what it looks like. You have your cameras, or really the software's directions of forward and sideways. And then boom, you have the reel that's just slightly off to the side. And you can sort of imagine if you're trying to analyze this movement and you use this, there's going to be some collusion between different directions. And your signals and your results that you get, it doesn't quite tell the true story of what the body is experiencing. So there's a mismatch between the axes or the directions in the space versus what the movements of the person that's going through. There's something different. And we have to address it before we go any further with our data processing. So one way to do that is to use a rotational matrix, which you guys have probably learned, but essentially it's about aligning, it's about changing the directions of forward, leftward, and upward, adjusting it however you want, so you go from your old, or really your camera-based, to your new, which is movement-based. That's one way to get your new set of directions. The other way would be to simply define it from scratch. And to do that, Evan, pay attention. All right, to do that, you are using linear and vector algebra methods. So let's go back to our example here. I literally had to do this, so it's very near and dear, close to my heart. The idea is we want to change our forward directions to respect which way the body is flying through the space. According to projectile motion, once the thing, you toss it, unless there's external force, its trajectory really shouldn't change that much, right? So that's a reliable way to make sure during the flight phase, this is the body's forward direction when it's flying. So essentially, we have to define a new forward axis, which we can take by computing where the body is at, and then finding a difference. Look at where it is in, by the end of the flight phase and the beginning of the flight phase, and that defines a single straight line that you can use to define your new forward. But how do you get the other two axes? At least what's nice is up is still up. The only thing that's changed is the horizontal. So now you have the forward and the upward axes defined, but what about the third? That's when you can use the cross product, and that's because we can make use of the special quality of a cross product, which is we feed it two initial vectors. Regardless of which way these are pointing, the cross product of them, the third vector, will always be perpendicular to the first two. So if you want a nice, right-hand rule set of angles that are all 90 degrees from each other, you just have your first two axes that already are 90 degrees, because one's horizontal, one's vertical. Just the orientation of that horizontal is a little different. You cross that, and you will always get your leftward axis. Okay. Hence, you make use of the cross product in order to get your new set of axes. So that's how you can redefine which way is forward and which way is left, based on whatever movement that we were studying. Another wrinkle to this is that this does not have to be the same for time. For Zahava and Aaron, who will be studying walking and turning, and we want to know with relative to the body, which way is forward, which way is leftward. Well, everybody studies straight line walking. That's easy. Straight forward is forward. But once you turn, then the forward and the leftward turns with the body. Okay. So this new axis definition can also be time varying. It doesn't have to be the same. For me, it was lucky that there is a single outcome, so I can make it exactly the same through time. And this axis is not just for the global directions. It actually is also used to define movements of the body segments. So here's just a quick example overview. In biomechanics, we want to know, let's say, oh, the side of my neck hurts, right? Then you have to say, what about what's the left side of the neck, right side of the neck? And then to really quantify, especially when you get into imaging, which you guys probably use for your study more, you have to define where things are, right? This is just a way for biomechanics people to say, okay, here's for the head, here's the different axes, the trunk, all of the body segments. And they all have their own individual axes. That also is different, left side to right side of the body. And then, so that's one part. The other part is to look at the joints. If you want to understand what the joints are going through, upper and lower, multiple different body segments, you also have to define the directions. And whatever comes with the axes, you have rotations about the axis. Okay? So let's say I'm looking at the forearm. It's the only thing, what I'm caring about in any movement is not just the translation of the forearm through space, right? There also is a bunch of rotation in multiple directions. Having these sets of axes and rotations about each of the axes essentially captures all possible movements so that we don't miss any in human movement. And this branch of math sort of comes from like aeronautical side, where the plane can flip whatever directions. Okay, so that was the linear algebra basis. So how do we actually use it in biomechanics? Let's say you do a cool thing, and you're like, oh, I wonder why my knee hurts. How would you get at answering that question? Let me sort that out. Let's say you wake up one day, you do anything, doesn't have to be dunking, and then you're like, oh, one of my joints hurts. How would you go about figuring out why and what to do? Yeah.
I guess I would think about like what I did the day before, what kind of like if there was like I banged it into something, or if I was doing some sort of movement that my body isn't used to.
Yeah. That's pretty much it, right? You think, oh, I wonder what my knees were doing the day before, or whatever activity that you think might be quite overly stimulating for the knees. And then as a broader question, you wonder what your body was going through, what kind of forces your body was experiencing. And that a lot of that is the essence of biomechanics. We want to understand what the body is going through in a variety of sporting movements, and especially, during the very specific phases, right? There are phases that are way more intense than others. For example, if you look at the landing that I have here compared to the takeoff, it's a lot stiffer, right? And there's also a greater degree of uncontrolled asymmetry. It just sort of happens with sport and life. So essentially the question is, how would you know what the body is going through? And some mechanics bases are that whatever you do in your body, Newton's third law, is that the force you apply by your legs that pushes down is the same as the force that the ground applies back to us. And usually in this sort of representation, we will show these as ground reaction forces. So if you take a look closely, over these little measurement force plates, you see as the participant takes off, little red arrows pops up, and that is representing the force that the ground is experiencing, which is the same as the force that they apply. To help with the visualization, we don't plot both because that would be too many directions. So this is usually what we represent. This is essentially saying, in order for the body to decelerate horizontally and accelerate upwards, these are the forces that's happening. And that's the way we sort of represent the movement. And lastly, the second law, which is, I wrote it out as all the forces my body experiences equals to the mass times acceleration. F equals ma, really one of the earlier equations you guys learned in physics class. And typically you have two legs in some way, which means every time you're interacting with the ground, it's going to have forces from either leg and your weight. And you essentially, all of locomotion is about overcoming whatever gravity is doing to you to trying to get somewhere, while maintaining balance, etc., etc. With 3D movements, this is when you have to define your directions, and that's how things tie together. So let's talk about how we actually get to the knee thing, okay? How we actually quantify the loads on a particular joint. So we call it joint kinetics, kinetics meaning force, joint, whatever joint of interest. So usually we start with the whole body analysis, and essentially the data we collected, we have data for the whole body, and as well as how the body interacts with the environment. Once we had that, we look into the subsystem or the limb level, okay? So each leg, if we're able to capture the forces, each leg has its own force that it experiences, and that force has to be supported or has to equal to the exertions from the sum of the lower limbs. That's the driving principle behind the joint kinetics. It's your entire leg working together to generate a specific force that allows you to perform a specific movement, be it walking or jumping. And further, you can understand what is each body segment, each joint doing by looking at the segment analysis. So in a link chain, which simply means a bunch of rigid segments connected by joints, you can look at each segment individually. And at the joint, you can split up the forces and the moments. So you can do analysis one segment at a time. Okay, so for the last part of the presentation, I'll sort of walk you through how we would approach getting to whatever's happening at the knee. We start with the foot. First, on the ground up. And here I'll sort of illustrate the axes or the directions for the foot in this bright yellow color. And this is multiple views, okay? One's a side view, one's a front view. And another fun thing is like the sets of arrows I did not label, that's based on the lower leg bone. So you can see how they don't necessarily quite align, where the leftward upward of the foot does not necessarily have to be consistent with that of the lower leg. And that's when you run into trouble with this sort of analysis, but it's the reality of the complexity of human body that we're dealing with. It's not a perfectly clean, like a hinge joint like a door. It's a complex set of bones that functionally roughly acts like a hinge joint. And one thing that we sort of define for dorsiflexion, plantar flexion, what's annoying is they have flexion on both sides. Typically, flexion only means one direction. So you flex your bicep, right? And then you extend your arms. But for the foot, it's one special case. So dorsiflexion, think of it as you picking up your foot. And then plantar flexion, think about it as you're pointing down. People say, if you guys have done like dance or martial arts, you might have heard people telling you to point your foot. That's the direction of pointing. But it's important to know which way it is, as well as the force in either directions. So here's what it looks like roughly. The math gets a little crazy here. But essentially, we first do our F equals ma, but only for a single body segment. So we have to capture where the ankle joint is at, the foot, and then all of the forces associated with it, as well as the segment's acceleration. And then we sort of, for the linked chain analysis, we say there is at the joint there is some sort of force that's counteracting both the ground reaction force and then the weight of the segment. And this is usually way bigger than the weight. So really, it's about whatever your ankle is doing to fight against the ground reaction force. Once you run that equation through, you can find this force at the ankle joint, and it's called the net force. It doesn't tell you how much your calf muscles is exactly doing, because it's a summation of the calf muscles at the back and your tibialis muscles at the front the sum of those things, that's what leads to the net force. So it's a gross oversimplification of what's actually happening at the ankle level, but it tells you overall what are they all trying to do together. It's the combined effect of all of the muscle groups. And then you do the similar things for the rotational aspect to get the moment, which is telling you, whether your foot is acting to point down or to bring it up. The equation gets a little crazy, but you have to basically account for them. And the easiest way to compute all of this is to make sure there are measures in the global space that you define. And guess what? We have to know, because sometimes your foot can point this way or that way in space. If you need to know whether you are acting to point toes down or bring it up, you have to rotate it back to whatever the axis system is for the foot. And so in this case, it's the attached to the foot. And then you just continue on for the shank and then the thigh, and eventually you get to your knees and the ankles. And it's not a simple process, but since we only have 1 to 3 segments as opposed to a snake robot which has 20, it's nicer. And the end result of that kind of analysis is something like this. Okay, so this is a result for essentially whatever the joints are going through. So you have your hip joint, your knee joint, and the ankle joint. And then there's also specific directions, like positive meaning you are acting to extend your leg, extend your hips, extend your knee, and then point your toes down. And then the other side. And you'll notice, it sort of starts small, goes up for the knee, but then for the hip it starts quite big, and then sort of stays steady, right? This is all essentially specific to the jumping movement. And by looking at this, you can potentially find locations where when you have really high knee moments, that might actually couple with specific ranges. For example, for the hip, this high peak is corresponding for when the leg is quite far in front of your body. And some professional level dunker actually mentioned that side of the hip is the one they feel sore after they perform a jump session the next day. And it's only that hip, it's not the other hip. Right? And you can see just from the size of differences in the loads they experience, that's quite different. Similarly, for this participant, at least the knee, those are actually quite similar. But depending on the configuration of movement, you can have one that's a lot higher than the other. And that's how you can find clues onto what kind of loads the body is experiencing during various kind of movements. In order to do this, though, you do have to capture the forces for the lower limb. Okay? So quickly to recap, directions are important if you want to figure out what the body is doing using biomechanical analysis, and we use linear algebra that accounts for directions. And here's an example for when people don't account for directions. All of these are supposedly the same exact variable. It's a sagittal plane knee joint moment when you're walking, and this is time normalized. So theoretically, the time shouldn't be an issue. But because people weren't clear about which way is upward, leftward for the knee, look at this crazy spread. If you show this to your professor, you won't be able to graduate unless you fix it. That's why it's important to make sure the coordinate systems and the directions are consistent and sensible. Okay? So it's supposedly simple, but we always need to be careful. And even for PhD students, we can make mistakes. Okay? So I hope that was interesting for how we do biomechanical analysis. I hope for people in the lab, that was helpful. All right, thank you.